In this video, we will study this problem that we stated during the introduction. Basically, that is the one-dimensional Dirichlet problem. So here it is. And I will actually simplify this problem slightly by choosing c equal to 0, so it's easier to actually show. But of course, this can be generalized to different types of problem. And again, our intent here is to show you how it works on this particular equation so you can adapt this methodology to other equations that might be similar, but of course different from this one. So let me actually start by stating c equal to 0. And so what I have here is this problem, minus u seconds equal f on the interval 0, 1, and that will be the open interval. And then on the boundary, I have boundary conditions, that is u of 0 equals 0 and u1 equals 0. F will be chosen in L2. So here's the regularity that I will require on F. It is not that demanding, but we need F in L2 to actually show the existence and uniqueness and continuity with respect to F for this equation. So what I would like to say, though, is that some of you might be thinking it's a little weird that we're actually doing all of this to solve this, to actually study this equation, because we know how to solve it explicitly, obviously. All you need to do is to take the antiderivative twice. So it's not exactly groundbreaking, but what I would like to say is I'm trying to explain to you how this works, and you can adapt it to more complicated equations. And also in higher dimensions, which we will do in next video, you won't be able to solve the equation explicitly. So what we're doing here is some merit, but I just wanted to point out indeed that some of you might think it's not a very complicated equation nevertheless. So what we are going to do in this video is to prove Wellposedness of this equation. This will be done in several steps. So let's get started with the first step. First step is actually not really part of the proof. It's what you do on draft paper. So on draft paper, you assume u to be C2, and you choose, of course, u0 equals 0 and u1 equals 0 as a solution. So you see, the reason why it's not part of the proof is because you're making an assumption which you cannot make at this point. You don't know if u is in C2. So you assume u is in C2 just in the first step so you can see what are the equations that will come out and how you can actually set up your proof. So really, again, that step one is somehow a preliminary discussion that somehow takes place on your draft paper, not necessarily on your actual proof. Okay, so now that I assume this, I will choose phi to be in C1c. That means a function that will be C1 with compact support. And if I choose that phi here, I would like to just go back to the equation I have, minus u seconds equal f, multiply this equation by phi. In other words, multiply both sides by phi, and then integrating over 0, 1. And then what I get is this, minus integral between 0 and 1 of u second phi equals the integral between 0 and 1 of f phi. Now what I can do is to use the Green's formula, also known as the integration by parts, and say that basically rotate the second derivative into the derivative on phi on my left-hand side. And of course what comes out is u prime 1 phi 1 minus u prime 0 phi 0 with a negative sign that was coming from that integral. And of course the integral, the negative sign has disappeared because you have minus by minus. So here's the Green's formula that you have. And of course, because phi is with compact support, what we know is that phi of 0 and phi of 1 will be 0. Subsequently, that bracket here will vanish, and I'm left with the integral between 0 and 1 of u prime phi prime equals the integral between 0 and 1 of f phi. This is what we will call the variational formulation, and this is what we are going to use in the next steps of this proof. Or actually, I should say, in the second step is actually really now is the proof going to start. So you can almost forget what we just did before. Just keep in mind the expression we found. And you could even say, okay, well, I'm not even going to tell you how I found this expression, but here is the expression I'm considering. I'm considering this expression. I have the right to do so. I'm just saying, okay, let me just out of the blue, if you don't want to tell us step one, which gave you that equality, let me consider the integral between 0 and 1 of u prime phi prime equals the integral between 0 and 1 of f phi. Okay, I can just write this equation, right? Okay, now what I will do is I will define a bilinear form A, which is basically the left-hand side, and a linear form L, which is basically the right-hand side. Okay? And then I will, since u vanishes on the boundary, then I will choose a space H that will be H10. And again, remember, we define H10 in chapter 3, at the end of chapter 3. If that is not clear for you, please watch this video again. So I'm considering H, which is H10, endowed with the norm H10. Okay, now A and L will be properly defined on H, right? U prime will be perfectly defined. If U is in H, in H10, then U prime is in L2. And if phi is, well, in H, then, well, that's in H10, so phi prime will be in L2. Now I have the product of two L2 functions. That's a L1 function, therefore I can integrate it. The left-hand side is properly defined. Same thing for the right-hand side. Phi is in H1, therefore in L2, and F was assumed to be in L2 as well. So again, the right-hand side can also be completely perfectly defined. So A and L are defined on H. So you see, by choosing this expression here on top, then what I'm saying is that I can, if I want, I can define this with A and L defined on H, and that makes sense. All right, now the problem I would like to solve is the variational problem called for all v in H, A u v equals L of v. That will be the variational problem associated to my PDE. And we will see that if I solve this problem using distributions, I will be able to recover my PDE. So I will be able to go from my variational problem, my weak solutions, to the actual PDE that I'm looking at. Okay? So that is step 2. Step 2 is basically putting together the variational formulation that is right here at the bottom. We have a problem to solve the variational problem. Step 3, we want to use the Lax Milgram Theorem. Therefore, what we're going to do is to prove continuity of A and L. Is A continuous? Well, let's look. Absolute value of AUV is, well, I replace AUV by its expression, and that obviously using Cauchy-Schwarz will be smaller than the norm L2 of U prime times the norm L2 of V prime, which is equal to the norm H10 of U times the norm H10 of V. Okay? All right. So if I have this, then obviously I do have continuity in H10, right? Because if it's equal, then it's small, I mean, smaller or equal than 1 times this product norm. So A will be continuous in H10 in my Hilbert space H. What about L? Well, using Poincaré now, I will have that L of V is smaller than constant times the norm of F in L2 times the norm of V in H10. Now, as you can see, that will give me continuity in H10, okay? What I have here is I'm saying that L of V in absolute value is smaller than a constant, which is C omega times the norm of L2, of F in L2, so that's that constant, times the norm of V in the Hilbert space I'm considering, and that is the norm H10 of V. So that tells me that L is continuous. Therefore, what I have is that A and L are continuous for that Hilbert space H10. All right, let's continue with step 4. Let's do coercivity of A. Again, we want to use Lax Milgram, so we better check every single property we need. What do we have? AUU is, well, simply the norm of U in H10 square. Therefore, it is coercive. That is not a problem. I would like to make a remark here at this point. What I would like to say is that everything somehow was just worked perfectly. And it worked perfectly because we found the right Hilbert space for this to work perfectly. And that's why we chose H10. That can be the tricky part when you have an equation, a complicated equation, maybe with, with complicating stuff. Let's just not point fingers here. But, you have a complicated equation. Then one of the difficulty you can have is to find the proper Hilbert space so that A will be continuous and coercive and L will be continuous. Obviously if we had chosen another space than H10, we would have had problems. And I suggest you just, at some point, when you're done watching this video, come back, watch it again, and think, well, what happens if I replace H10 by H1, or by L2, or by something else, and see where it doesn't work and why it's a problem. All right, now we're really close to applying Lax Milgram. That's going to be step 5. We're going to show that we have existence and uniqueness for the variational problem. And the way we're going to do this is simply by actually applying the Lax Milgram theorem. We are in the setting where we can do that, right? The problem we're trying to solve, the equation is for all V in H, AUV equals LV. So that's exactly the problem, the solution, the equation that we want to solve. Don't get confused with the notations. What was called U is now called V. It's not a problem. You need to be sharp on this, and you need to kind of be able to change notations all the time. So what we're saying is, if you look at this equation, that's exactly the equation that appears in the Lax Milgram theorem. Now, what do I have? H, that's a Hilbert space. A, bilinear. H, linear. And it's also continuous, both of them, L and A. A is coercive. Well, let's apply Lax Milgram. There exists one and only one solution U in H such that this equation is satisfied. And you know what? On top of this, you have that AUU equals L of U implies, in other words, a U is a solution to the U is a solution, implies the norm of U in H, H10, is bounded by a constant times FL2. Well, that's pretty nice, isn't it? So what we're saying is that the variational formulation is well posed. At this point, we proved the existence and uniqueness of the solution to the variational problem. But some of you are probably thinking, okay, well, that's not the problem we had to begin with. The problem we had when we started was not the variational problem. The problem we had was a PDE. How do I get from my variational problem to my PDE? Well, you see, last week when we did chapter 3, we actually introduced distributions, right? And that's going to turn out to be useful now. Step 6, we're going to solve the PDE in the space of distributions. A little bit like, when we go to C and then we go back to R at some point, right? That's what we're going to do now. All right, so what happens is that the space of bump functions is included in H10. So what I'm saying is that obviously what I have is, if the variational formulation can be applied for all elements in H1, 0, then it must be true for a subset. And so for all phi in D, then the integral of 0, 1 u prime phi prime equals 0, 1 f phi. Okay, so that must be true. Which is the same as writing this as the bracket u prime phi prime equals f phi. And you see here, I'm saying that if phi is in D, then really I can consider u prime as a distribution, right? I mean, this is exactly what we had last week in chapter 3. So I'm writing this simply as a distribution. U prime is, well, you know, I mean, it's L1 log. So, I mean, I can really consider this as a regular distribution. And I'm just saying that I'm going to have this here. Okay, when I do this, let's see. I can actually just say that u prime phi prime, that's going to be minus u second phi prime, right? I mean, that's in the sense of distributions, of course. I mean, u second may not be a function. There is no reason for it. So what I'm saying is I'm just writing this in the sense of distributions. Now, when I'm writing this in the sense of distribution, and of course, I mean, I can just put everything on the left-hand side, what I end up with is minus u second minus f distribution applied to a test function phi equals 0. Okay, therefore what I have is minus u second equals f in D prime. And the reason why I have so is because I have minus u second minus f, which is applied to any phi is equal to 0. So I apply to every single phi. So in the dual space, it means that, which is distribution, it means that minus u seconds minus f has to be the distribution 0. Therefore, I can write that minus u seconds equal f, and again, in D prime as a distribution. So I left the space of functions, which I'm allowed to do, because I'm going into this bigger space, and in this bigger space, I can guarantee that minus u second equals f in D prime. And I have, as an hypothesis, u of 0 equals u of 1 equals 0. All right. Now, let's just summarize a few things here and just go to the next step, actually. What do I have? I said that we had u in H1, right? That's what Lax Milgram gave me. I had u in H1, or H1, 0. I mean, you know, because u is equal to 0 in both ends. Okay, so u is in H1, which means that u is in L2, and u prime is in L2. That's the very definition of what H1 is to begin with. So if u is in L2 and u prime is in L2, let's see what happens. I have a third thing that I need to take into consideration, which is that minus u seconds equal f, in the sense of distribution, of course, but I know that f is in L2. Oh, so that means that u second is also in L2. Okay, so let me recap this for a second. So we have u in L2, we have u prime in L2. By going into the distribution, we just found out that actually we had negative u prime, which is f, which is in L2. So u second, I'm sorry, is in L2. So u prime and u second are in L2. Okay, well that must be so that u is in H2, right? So we have u in H2. Okay, and of course we can also apply the Poincare inequality again and actually write this here. So what do I have? Well, I actually have a solution in H2. Okay, so you see what we have now. What we're saying is that u, which was a distribution just a few minutes ago, is actually a distribution that happens to be in H2. Oh, so actually it is a function, right? I mean, you know, it is a function. We just found out it's a function. All right. Now, what happens is that if f is continuous and in L2, then the solution u is a classical solution to the problem. So actually, the PDE has a solution. So what did we prove here? We proved that if F is in L2, the problem find a solution U in H2, which is also in H1, 0, such that minus U seconds equals F in 0, 1, and the boundary condition U of 0 equals U of 1 equals 0 is well posed. There is a constant C omega, which is strictly positive, such that for any given F in L2, there exists a unique solution U or UF in H2, and which is also in H1, 0, that is continuously dependent on F. And we have this inequality. So this is what we prove. All right, so here's the steps that we basically went through, 7 steps, even though step 1, again, was not really part of the proof. It's something we did on the side to figure out what was the A and L to choose. So really the proof was steps 2 to 7. Here is basically the list. First, we found the weak formulation. Then we wrote the variational formulation. Then we proved continuity of A and L. Then coercivity. Then we applied Lax Milgram. And then we got the solution in the sense of distribution and got the regularity of the solution. This obviously is something that you need to work on very, I mean, you know, just take the time it takes to really understand every single step. Here's a handout so you can really have all of the equation and really work hard on it. You need to understand this completely. So look at the handout, make sure you understand. And in the lab session, we'll do a few things. We'll basically try to tweak this proof for other problems that are somehow similar. The non-homogeneous Dirichlet boundary condition, in other words, instead of having U of 0 and U of 1 equal to 0, the homogeneous Dirichlet boundary condition, which vanishes on both ends, then we have A and B. And also we add up a C here, Cu in the mix. We also do non-homogeneous Neumann boundary condition. That means that we have the derivatives that will be provided at both ends. Also, we'll have a mix between the Dirichlet and Neumann. And again, we have C in the equation. So all of these interesting problems will be done during the lab session. And that is a way to tweak the method. And again, the method we just gave can be extended to very many types of problems. And of course, well, I'm not saying it's easy to adapt it, but obviously it's a method that is quite useful for these problems. Now, before we end this video, I would like to show you 2 things. The first thing is, actually numerically, we just took this equation, and I would like to thank Pauline Lafitte for providing these graphs. Minus U seconds equal F, and here's an F that was generated. It's an L2, but it's really an ugly F, and it's very irregular, but it's L2. Okay, so you basically run the program, and we'll see how to do this in the very next chapter. In chapter 5, we'll do finite element methods, and you'll know how to run these simulations. But for now, just trust me that we did that properly. So we have this F, and we actually let me actually show you this U prime. So it's obviously much more regular. It's basically in H1. And here is U, which is both in H2 and in H1, 0. And let me actually put all of these equations, these functions together just to show you how irregular is F and how regular is U. That's the first thing I wanted to show you. Second thing I wanted to show you is that F here is non-negative. And what happens is U prime is decreasing, and U is non-negative, and basically what we have is U of 0 equals 0, U1 of U of 1 is equal to 0, and that will actually lead to something we'll discuss more later, which is the maximum principle, which states that if F is in L2 and it is non-negative almost everywhere, then the solution U in C1 of the Dirichlet problem is non-negative on 0, 1. And there are a lot of applications in modeling for physics. One of them is that if you actually turn on the heater in your apartment, then the temperature will rise.